Stanford University.
We have a program on low-cost flywheel energy storage. The nature of this program is we're combining the equipment expertise at the University of Texas at Austin with materials expertise that we have at UT Dallas. And again, this program, the GCEP program, is so extremely impressive. I was amazed at the lectures and discussions that I've heard. So again, the concept here is to, now I can't find my pointer, oh here we go, to make devices, flywheel batteries, that both store energy and then convert it mechanically and then convert it back to electrical energy. Now, to store electrical energy as mechanical energy and then convert it back to electrical energy. The reason for these flywheels is, of course, the need to improve the stability, the power quality and reliability of the electrical grid, which is very well described in the last talk. And again, there are special problems with using renewables for the grid, and this is to help solve these problems. Why flywheel technology? Nearly all electricity is used in motors. Nearly all of the electricity in the world is produced from generators, and about 60% of the world's power is used in electric motors. Again, emphasizing the importance of rotating machines that are part of the grid today, and there's clearly a need for a revolutionary storage technology that can provide a highly effective means of storing energy that can be perhaps collected by solar energy or from wind energy. This is a highly integrated team effort where the work on the flywheel, specifically for flywheel design and other types of studies, particularly focusing on the non-materials aspect of the flywheel, will be done at UT Austin, and at UT Dallas, we're basically working on materials, improved materials that can be used for flywheels and other types of energy applications. Now, I know that most of the talks we've heard today have been very broad perspective type of talks, considering broad issues. Now, I'll go down to a new technology for energy that we recently invented. This work was published in Science in January. This new technology enables to take, for example, high energy capable materials for batteries that are powders, or high energy storage capability powders for high storage capacity powders for example, hydrogen storage, or magnetic materials or superconducting materials, to incorporate them in a yarn as a powder. This yarn can contain up to 98 weight% powder. The resulting yarns are knittable, knottable, sewable, weavable. You can, for example, for a battery or a biofuel cell, they're very easily woven into electrodes. And we've demonstrated these yarns for such applications as superconducting yarns, high-performance lithium-ion battery electrode yarns, catalytic fuel cell yarns, and yarns that comprise graphene. This new technology is based on transparent sheets of carbon nanotubes that are shown here. We draw these transparent sheets from carbon nanotube forest. These sheets are a strange state of matter. They're an aerogel, which as we draw them can have about the density of air. If we use tricks, we can obtain these aerogel sheets that have about the pound per pound strength of steel. We can obtain them as having a density that's 10 times less than that of air and 10 times lower than any self-supporting aerogel previously known to humankind. These sheets have so low a mass per unit area that 44 ounces of these sheets would cover an acre. Now, the article that just came out that we're just doing the first press on is really using these carbon nanotube sheets to make things disappear. Right now we're making things disappear underwater using the mirage effect, in which these sheets, the very high surface area, the very low aerial density of these sheets make them superb for making very sharp temperature gradients. And as I'm walking to this conference, I thought it would be very nice if we could provide a similar technology for cloaking windmills, and perhaps it is possible. Our technology takes these carbon nanotube aerogel sheets, and here we go, which we draw from forests of nanotubes. When I say a forest of nanotubes, I mean a bamboo-like forest in which each of the trees is a cylinder of carbon, in other words, a nanotube. What we can do is when we draw these sheets and twist them to make yarn, before we insert twist, we can put powders on them. These powders can be superconductors, magnetic materials like soft and hard materials for spring magnets, battery materials. It could be horse manure. And people tell me I would put camel dung in, Biscroll camel dung into our yarns if it was practically useful. Sometimes I make spontaneous comments that sometimes I wish I hadn't. But there is truth in that comment. Now, these powders are trapped in the scrolls that I keep on losing my pointer. There it is. They're trapped in scrolls that can have either Fermat, Archimedean, or dual Archimedean structure. And this illustration, this schematic illustration of a Fermat scroll is very illustrative and it does not incorporate the fact that in the real yarns that can have the diameter of a human hair, there are maybe 100 layers of this guest, this carbon nanotube, the host carbon nanotube sheets, which is confining in a very substantive way the powder. And so we're producing multifunctional yarns, which we believe will have a very important part in the energy future of our country. Or as another way of inserting twists, we can draw carbon nanotube sheets out from our forest. We can draw these sheets out at 2 meters per second and insert twist either before insert twist right away or draw the sheets and then electrostatically paint using a paint gun the desired guest material. Now, again, depending upon how we insert twist, if we insert it symmetrically by drawing from a forest, we get this Fermat type of scroll geometry. If we insert it symmetrically between two rigid supports, we get this Cornu topology, which is basically a double Archimedean scroll. And we can change either of those topologies to just an Archimedean topology by pulling asymmetric. We can put the guest material on carbon nanotube sheets in any way we want. For example, we can electrostatically paint on just one part of the sheet, or we can paint using a inkjet printer so that we get whatever pattern we want to. And this is important. For example, we're using our carbon nanotube sheets and yarns for Grätzel solar cells. In that case, you don't want to have the light in the, you don't want to have the TiO2 that's used for these Grätzel cells, or what's also called dye solder cells, in the center of the yarn where the light is already absorbed. You want to have it on the outside. So all we do is put the guest on one part of the sheet before we insert twist. Now, this is even after, for a yarn that contains 90% colloidal SiO2. They remain flexible enough to tie into this very tight knot. We can, again, sew them, these yarns containing this guest inside the @ sign, moldable nanotube host. We can easily sew it, for example, into Kevlar textiles. Here we've show pictures of single-ply, 2-ply, and 4-ply yarns of, that are guest-free. The guest-containing yarns look similarly. Here we show the first nanotube yarn textile that we fabricated. This was fabricated by one of our high school student nano explorers. Her picture was in Science as a consequence of this breakthrough of making this first textile. My picture has never been in Science. Can Biscrolled yarns be washed? This is interesting, for example, in some personal energy type of applications, such as electronic textiles. We can take a 6-centimeter length of this yarn, twist it around 1,100 revolutions per minute for 3 hours in hot, soapy water. We don't lose guest significantly, measurably. The material doesn't change in terms of its appearance, and it doesn't decrease strength. We have various methods for making our biscrolled yarns. We can deposit materials most attractively most conveniently by electrostatic painting, but we have a variety of other ways to deposit these guests on top of the carbon nanotube sheets, and some of those methods are indicated here. In a simple way, we're doing our biscrolling now. We can just draw a sheet web from a forest. At the same time, we're inserting twist, and we deposit the guest on this web. I'll show you a picture of our carbon nanotube guest, the guest for our carbon nanotube yarns being inserted from an aerosol. Here we have a tube which is containing hydrogen and titanium tetrachloride. They're mixing, forming an aerosol. This is looking down the edge of the sheet. This is an exhaust tube. This is again, this is the yarn viewed on top of it. What you don't see is my postdoc's hand. He's in this case just pulling the web along as the guest is being deposited. Of course, this is easily automated, and we have done that. Now it's not hitting the web, but as soon as it hits the web, you'll start seeing the guests being deposited. Very convenient. Again, we can draw these sheets at up to 2 meters per second. Now, so far, I've talked about making biscrolled yarns using carbon nanotubes, in particular force-strong carbon nanotubes. We've demonstrated we don't have to use force-strong carbon nanotubes for our process. For example, we can use nanotube sheets that are ultra-thin. They have to be ultra-thin. That are, for example, made by David Lashmore at his company NanoComp. So again, from a viewpoint of upscaling for the program will be both upscaling our own process, but also using materials from Nanocom. Moreover, this technology does not need carbon nanotubes. The point is, in a yarn that's the thickness of your hair, I don't talk about my hair, we have about 100 layers that are scrolled together. And trapped within these scrolls, we have the nanoparticles or larger size particles. Now, so the individual sheets must be very thin. Our sheets, when they're densified, are only about 100 nanometers thick. Now, what we can do is we can take our carbon nanotube sheets, template them with metals or with ceramics, or we can, particular metals, we can, with magnetic materials, and then in some cases, we can remove the carbon nanotube core. So now we have, for example, a sheet of a ceramic material, such as shown at the top side part of the slide. Here we go. And now we can twist, spin this material. I wish this pointer wouldn't disappear. Here we can twist it into a yarn. We can take a carbon nanotube sheet and the ceramic sheet and biscroll them to make a material that has a cross-section like this. We can template with gold and remove the carbon nanotube core, so now our yarns are gold yarns of gold nanotubes. Here we show two carbon nanotube sheets that we cross-plied and removed the carbon nanotube sheet. You can see from this templating, which is conformal in nature, we can get welding between our nanotubes. And we can also play this game with graphene sheets we can grow graphene on a copper sheet by known technology, put two carbon nanotube sheets on top, put this assembly in a bath containing iron chloride. The copper disappears. We end up with just a one carbon graphene sheets sandwiched between, supported by two carbon nanotube sheets, and then we can twist them into yarns. We can make superconducting yarns very easily. All we do is take, for example, magnesium and boron micron-sized particles and deposit them on top of the carbon nanotube sheet, twist them into the yarn, put the yarn into a cryostat, and this is what we obtain for magnesium diboride. I missed the, we need to anneal in that particular case, whereas we're initially biscrolling magnesium and boron, so we have to heat them up in order to form magnesium diboride. This contrasts with a conventional way for making superconducting wires, which is to put powders inside tubes, draw these tubes, group the drawn tubes together, draw again, group them together, draw again, 30 times in order to make cables of superconducting wires. This is a part of our program that will be started tomorrow, how to increase the current carrying capabilities and the temperature capabilities of our biscrolled superconducting yarns. We can take our biscrolled yarns and make superb materials that are catalytic for fuel cells. The fact that if you nitrogen dope carbon nanotubes, you form a material that's highly catalytic for use in an oxygen electrode on a fuel cell is not new for us. But what we've shown is a way to provide this highly catalytic material and a useful material for fuel cell applications. Now, modification, we can make the yarn itself before we twist it, before we biscroll the guest inside, we can make it nitrogen doped by exposing the carbon nanotube sheet to a ammonia plasma. And here shows nitrogen doped carbon nanotube yarns. In collaboration with our colleagues at Hanyang University, we've taken these nitrogen doped carbon nanotube yarns, that we inside which we biscroll different catalysts depending upon where we're talking about the anode or the cathode. And then, since we're using different catalysts for anode and cathode, we can use a single compartment fuel cells. We've created a fuel cells in this very initial work, which is has a slightly higher power output than has been previously reported in the literature, and that was a very recent report in Nature Communication. Biscrolled yarns, battery materials, very exciting area for us, and I think for many people. Again, I show a picture of our nanotube yarn textiles. For example, biscrolled, we previously made textiles that contain supercapacitors, and that's shown on the top here. This is two yarns that we plied together with a separating electrolyte, and these are carbon nanotube-based yarns. This yarn functions as a high energy storage capacitor. Another yarn we inserted in the orthogonal direction. Now, what's the problem with the highest performance energy storage materials for batteries? The problem is, in many cases, like the case of lithium iron phosphate, even though they have really fantastic rate performance, they have high energy storage performance, but they have lousy electronic connectivity. By biscrolling these powders in carbon nanotube yarn, we provide intimate proximity, nanoscale proximity between the powders and the host. The lithium iron phosphate powder and the carbon nanotube host, which is highly conducting, and solve a problem that's just major in the battery area. In the battery area, in order to collect electrons or holes from the lithium iron phosphate, you need connectivity aids. You need a binder such as polyvinyl difluoride to hold together this powder of the redox material, and a connectivity aid like carbon black. Then you need aluminum foil that supports this structure. If you add all the weight penalties from these materials that we can eliminate, they are very substantial, about 30%. Here we show a yarn of our lithium iron phosphate on the top. This is, again, this yarn was actually knotted after we used it for a battery. It's just remarkable. You know, sometimes God gives you great gifts. And the discovery of this was a gift of God, because we didn't anticipate that these biscrolling process would provide performance anything like this. It was just luck, depending upon another way of phrasing it. We see very good performance in our initial measurements on lithium iron phosphate as a battery materials. These are initial results, but they're attractive. We're now biscrolling silicon, for very high performance anodes. This is a cathode. There are lots of applications possibilities for our biscrolled yarns, and I won't go through them. Some of these we demonstrate, others are in a process of demonstrating. I just want to say I haven't covered in any way the material scope of what we'll be doing for the GCEP program, which will be involving making very strong composites for flywheels using our carbon nanotube yarns, which will involve, again, superconducting yarns, magnetic yarns for the flywheel capacitor. And thank you very much for your attention. Yeah, the challenges. Pardon me? Can you repeat the question? Ask me a question.
No, he said repeat the question.
Well, let me ask a question.
Okay.
In hearing this presentation, you're very excited about this, obviously. It sounds very exciting. In hearing your presentation, you're very excited about this, and it sounds very exciting and cool work. What would you say are the disadvantages in using this?
Right now, until the cost goes down for using carbon nanotubes as a reinforcing element for flywheels, the major disadvantage right now is cost. The cost of even moldable nanotubes is about $50 or $75 a kilogram. Now, we would like to bring down that cost. The challenges are, if you want to obtain carbon nanotubes in specific forms that are most useful, then the cost can go higher. Right now, we are producing small quantities of the Biscrolled yarns and sheets. We have not upscaled, so developing technology that enables upscaling can be very important. And in the challenges for obtaining performance other than structural, structural is a big game. A big win here is important in changing basically many aspects of industry. I mean, from some of our major funding sources are aircraft companies for obvious reasons. The opportunities, but then there are enormous electronic opportunities. In the present program, we're going to be using them to make, again, the superconducting yarn and the materials that are magnetic yarns.
So in terms of thinking about taking these yarns and I guess, how would you go from these yarns to, a very large flywheel structure made of these? What's the manufacturing process?
That's a good question. There are two ways that I think are particularly attractive. We've already made some composites in which we basically just draw the sheets off from a forest and impregnate them with a resin. And this gives attractive toughness, attractive modulus, attractive strength, but we want to increase all of these aspects. You don't want to have a flywheel that's brittle. One of the remarkable aspects of carbon nanotube composites, this is an aspect that we demonstrated in 2003 for yarns made in a different way, is they can have toughnesses that are about over 5 times higher than that of spider silk. And spider silk is by far stronger than yarns made by humankind until our work. So our flywheel is not going to destroy itself as catastrophically as would a brittle material. Again, how do we make these flywheels configurations? You will want to have anisotropic mechanical reinforcement so we can ply our carbon nanotube sheets so that we get the high strength direction where we want it. We also can use wovens technology. In other words, we can take our carbon nanotube yarns, weave them into woven structures, and then use infiltrate polymers to form composites.
On your superconducting fibers, what sort of current densities have you achieved and expect to achieve between 20K and, say, 35K?
This is the big plus of magnesium dibromide. It has fantastic current carrying capabilities. The Japanese, I've been told by the Japanese they're going to be using the magnesium diboride for their levitated trains, but I don't know if that's the fact. but I have been told that. And not because it's a high temperature superconductor. It's a low, it superconducts at 40 degrees Kelvin. The problem is these wonderful high temperature superconductors suck when it comes to current carrying capabilities. In the GCEP program, we want to eliminate this problem. We want to have high current carrying capabilities at higher temperatures. But to directly answer your question about present current carrying capabilities, our current carrying capabilities at present are lousy.
All right.
Thank you very much for your attention.
For more, please visit us at stanford.edu.